My goal in this video is to show the derivation of the energy of a hydrogen atom, or the energy of the nth Bohr orbit, and eventually to derive where this equation over here comes from. We're going to start a technique very similar to what we did, in fact the same technique that we did in the last video, with using Newton's second law, Coulomb's law, and centripetal acceleration. Since we know we have the electrostatic force of the electron and the proton, and we have centripetal acceleration as the electron seem to be orbiting in a circular motion. And by using Newton's second law and replacing F with Coulomb's law and with A with centripetal acceleration, we get to this point, which we're going to come back to in just a moment. But because we're interested in energy, we could start with the total energy being the sum of the potential plus kinetic energies. And just a real quick side note about the potential energy, it's going to be the accumulation of the static electric force. And so we could go ahead and show that the integral of that, ke squared, we could say that that's r to the negative 2 dr. And by using the power rule, we've got constant, constant. Remember, we're going to add 1 to this, so it's going to turn into negative 1 divided by negative 1, and then plus a constant. And so this is going to be our potential energy. And we could do divided by r. And then our kinetic energy is going to be the accumulation of momentum with respect to velocity. Power rule with v, so this is going to give us, it's going to be v squared divided by 2. And this is our kinetic energy. So just a quick recap there to see where all these come from. Now at this point, if we're trying to get to this equation over here, we notice that, well, there's no velocity. So let's start with that. In fact, we could even identify this whole mv squared right here. Let's multiply that r over. And so really mv squared is going to equal k e squared over r. So let's go ahead and substitute that in for this term. So we've got negative k e squared over r plus, I'm going to call this 0.5 times k times e squared, all divided by r. And it's beautiful at this point because we can now use common denominators and combine the numerators here. So we'll go one more step. Negative 1 plus 0.5 is going to end up getting us negative 0.5 k e squared, all divided by r. So now at this point, we could use the radius of nth Bohr orbit to make another substitution. N squared h squared divided by 4 pi squared times m times k times e squared. And this is actually what we're now going to replace for this r down here. So let's go ahead and come up this way. Starting off with what we just had. If we divide by this fraction, we know it's the same thing as just multiplying by its reciprocal. So we'll go ahead and flip that. 4 pi squared m k e squared over n squared h squared. And hopefully at this point you're starting to see that we're making significant progress, because the energy formula is, we're very close to deriving it at this point, n squared h squared in the denominator and so on. So one last step here. Negative half of 4, negative 2. And then let's combine what we've got. We got our k squared. We do have just a pi squared. And e squared e to the 4th times m all over n squared h squared. And again, we could just rearrange it so that it matches with this perfectly. So let's just go ahead and do that. Oops, I'm sorry, I threw in another negative there. That shouldn't be. So we have now negative 2. We do have the pi squared like we have here. We do have the m, the mass of the electron. We have k squared. And finally, we have our e to the fourth. So hopefully this is somewhat satisfying that we were able to use substitutions in order to get this far. And then again, we could, since these things are all constants at this point, we could go ahead and substitute for everything, and we could get the energy of an electron in the first energy level, and that would get us negative 13.6 electron volts. So like we said, that would end up being the energy of an electron in the first energy level. I hope you found that helpful, and I'll see you in the next video.